right, this is the last of the videos for Chapter 4 summary notes. This involves periodic property trends, and we'll talk about 4 of these. And the first one that we talk about with the periodic table are the valence electrons. Valence electrons are those that are found in the outermost energy level of the atom. They are always the S and P electrons. All right, valence electrons are always S and P. Always S and P electrons. Okay, always S and P electrons. All right, because the D sublevel always fills in after the S's, so that's why it's always winds up being the S and P sublevels. All right, so there's a little chart here on your screen that shows the representative elements with a generalized formula at the top of 2 of the columns. All right, we're going to fill in the rest of the columns, but I think you'll see a pattern if I fill in the very last one, all right, which is column 18 or 8A. All right, notice what happens. I'm sorry, let's get it in there right. N stands for the level, the row that it's on. The S block is filled up, and the P block is also filled up. All right, so I'm going to expand this one because it really should be NS2 and P6. Sometimes you'll see it written that way. Sometimes you see it with just the N in front of both the S and the P's. All right, so these are the generalized electron configurations for an entire column. All right, so the trend would be on the periodic table going from left to right that valence electrons increase. All right, they increase as you go from left to right on the periodic table. Okay, left to right on the periodic table, the valence electrons increase until you get to 8. Okay, so if we take a look at the valence electron configuration for calcium, all right, we can find calcium, it's in the 4th row. All right, so we want to write down its N value, which is 4. It's on that 4th row. It's in the S block of elements, and it's in the second of those S blocks, so we write 4s2. All right, so we can fill in the NS2 up here because that's where we found calcium. We found calcium at 4s2, where N represents the main level of energy we can find the element on. All right, then if we do lead, lead is on the periodic table at 82. All right, it's on row 6. Okay, it's on row 6. All right, or column 6, I'm sorry, it's on row 6, and it happens to be in group 14 or 4A. All right, so it's going to be here in the generalized formula, NS2P2, let me squeeze an S in there, P2. So for lead, it's going to end in row 6, so it'll be 6s2, and then I'm going to make a space here because you'll see why. Maybe you can guess why. All right, so if we take a look on the periodic table, and I'm going to scoot up to a periodic table here, all right, and show where lead is on the periodic table. All right, we said it was in column 14, so I'm going to mark it right here. Here's where lead is. Okay, to get there, we have to go 6s2, then we fill in the 4f14, then we come back into the periodic table, 5d, and then over 2 more to get that electron configuration. 6s2, 4f14, 5d10, and then 6p2. But again, the highest main level electrons are the S's and the P's. All right, now I'm going to come back down. All right, so 4f14, 5d10. Okay, but again, it's the 6s2 and the 6p2 that represent the valence electrons for lead. Okay, all right, so Lewis symbols, they're kind of a shorthand way of showing the valence electrons around a chemical symbol. And there's no more than 2 on a side, there's no more than 8 total, and we're going to do carbon as an example. All right, we use carbon a lot throughout these videos, and there's a reason for it. So carbon has 6 total protons, which means it has 6 total electrons, but it only has 4 in the outer main level. Remember, its electron configuration is 2s2. I'm sorry, 1s2, 2s2. I'm already jumping to the valence electrons. And then 2p2. So its valence electron configuration is 2s2, 2p2. All right, so how many valence electrons does it have? Well, I can count these and add them, which is 4 electrons. Or I can just go to the group that we find it in, which is 4a, or 14, and I know there. The group number tells me how many electrons there are. So how would I put them on here? All right, we can show one on each side. We can do it that way, or we can do it like this. Let me switch to the other pen. Trying to show. Okay. We can also show it, come up here. It depends on what kind of modeling you want to do with it. All right, just as long as you don't, this is something you don't want to see. All right, you don't want to do that. Okay, so one on a side or two on a side, and each one, another variation can be 2 here, 1 here, and 1 here. When I was back in high school in the ancient days, we did the s electrons on the right-hand side, and we distributed the p around the other 3 sides. But they tend not to do that anymore, so there you go. All right, so it says write the dot structures for sodium, aluminum, phosphorus, and argon. Remember, it's your group number at the top that tells you how many electrons to put around your symbol. Okay, so stop the video and take a moment to do that, and then come back. All right, element sodium has only one valence electron, so we'll put it there. Aluminum is in group 13 or 3a, so it's going to have 3 electrons. You can write it like that, or you can put one around each of the 3 sides. That's fine too. Interesting, phosphorus will have 5. All right, phosphorus will have 5. 1, 2, 3, 4, 5. And then argon's going to have 8. All right, so I'm sorry, I'm already putting a bracket around it. Argon's going to have 8. 2 on each side. Okay? You don't want to ever put more than 2 on a side. So that's how you do dot structures. Okay? Lewis electron dot structures. Ionization energy, it tells you how much energy is needed to remove one of the electrons from the outermost level. And there's a little equation that's showing you that. All right, ionization increases as you go across the periodic table. It's much easier to take electrons off the metals. All right, it's easier on the left side, and it's extremely hard for your noble gases to remove electrons there because they are very stable as is. The ionization energy decreases as you go down a column because that electron gets further and further away from the nucleus, from the positive attractive force of that nucleus. Okay, so the further away, electrons are further away from the positive force in the nucleus. Okay, metallic character. All right, develops more as we go. I'm sorry, metallic character develops more if electrons are easily removed. So again, the element that's way down here would have the easiest chance of having an electron removed because that electron would be the furthest away from the nucleus. All right, and metal characters decreases. We know these are the metals and these are the nonmetals. The metalloids are in between. And then we have those noble gases that are nonmetals, but they are stable as is because they're S2P6 arrangement. Atomic size, if we take a look at the atoms, it makes sense that they're getting larger as they go down because you're adding a main level of energy as you go down. All right, and as you go across, it might not be as easy to think about. They tend to get smaller as you go from left to right. I call this the snowman rule. It's easy to remember. The snowman is bowing to the noble gases. All right, because the noble gases are over here. So the snowman is bowing to the noble gases. Because it's harder to think about why is that doing that? And it's doing this, they're getting smaller because the positive force of the nucleus is pulling the electrons in closer. Even though you're adding electrons to the outermost energy level at the same distance, though, that's the important thing. If they're adding electrons at about the same distance away, but the positive force of the nucleus is increasing. All right, it's increasing. Okay. All right, so there's two little sets to try. All right, I'm going to stop it here and then you can come back and check your answers. Okay. Okay. All right, let's go through your answers and see how you did. All right, largest atomic size is sodium out of the group because the group is starts with sodium on the left, then magnesium, and then sulfur, chlorine, and argon. They are in that order on the periodic table. They're all in row 3. So they're all row 3 elements. Row 3. Okay. Ionization energy is the highest with argon, all right, because it has an S2P6 arrangement. Okay. The halogen was chlorine, 14 electrons was silicon. Just finding the element that's in this location, group 6A or 16, is sulfur out of the ones that were given. The most metallic character would be sodium because it's leftmost on the table. 2 valence electrons, magnesium because it's in group 2A. All right, the second set is kind of the opposite. We're looking at the smallest atomic size. That would be xenon because it's all the way over there on the right with the highest number of protons pulling in the electrons at about the same main level of energy all the way across that row. Alkaline earth would be strontium out of the group that's up here. All right, rubidium, the metalloid is tellurium, all right, because it's touching the staircase. Rubidium has the lowest ionization energy out of the group. It's the lowest one in that particular group. Okay. Tin is the element that's in group 4A. The least metallic character is xenon again because it's over there with the noble gases. And 7 valence electrons for iodine. Iodine's in column 7A. All right, so that's periodic trends, the valence electrons, Lewis dot structure, atomic size, ionization energy, and atomic size. Don't forget that snowman rule. That's a really good one to remember because it's kind of counterintuitive as to what happens. And that's it for chapter 4.